Sí, sí. Okay, good morning to everybody and welcome to the Severo Ochoa seminars of the Instituto de Astrofísica de Andalucía. Our speaker today is Rafael Luque. Rafael got the degree in physics in 2015 from the University of Granada here in Spain. His master's degree in physics in 2017 from the University of Heidelberg in Germany, and his PhD degree in astrophysics in 2021 from the University of La Laguna in the Canary Islands, and all of them were awarded with honors. He has carried out research stays in Mexico, Canada, the Canary Islands, Germany, and France, and he's currently a postdoctoral researcher of the Department of Astrophysics of the University of Chicago, and also at the same time he has a close relation to the IAA thanks to the Doctor Vinculado figure. His research field is focused on the discovery of an in-depth study of exoplanets. He's a member of different scientific collaborations like Carmen's tests, etc. And he has more than 100 publications, especially in the last years, in the field of exoplanets. In addition to his research activities, he has a strong commitment with outreach, having organized a number of public observations, star parties, and different workshops related to astrotourism. In fact, also, he has been managing the Starlight certification for several hotels and rural houses in the province of Granada. Currently, in this field of astronomical outreach, he works as the director of the Department of Research of the Novel Amateur Astrophysics Complex here in Granada. Today, he will talk to us about the demographics of small exoplanets. I'm sure that it will be a very interesting talk. Thanks, Rafa, for being here, and the floor is yours.
Yeah. Hello, everybody. I'd like to thank Anton for the introduction, also Pedro and the Severo Ochoa board for inviting me to be here, coming back home after a while. So yeah, I will present you today some results in general about the demographic of small planets. I know the group of exoplanets in the IAA is productive but small, so I hope to reach a bigger audience and get some general basis of what we do in this field and what are the current state-of-the-art research. So I will start with a nice video. This is not working, so yeah. So here you can see an animation where the discoveries of exoplanets are written as a function of their position in the sky, but also here we can track the number of exoplanets, how it is increasing over time. And color-coded are the points by the technique that has been used to detect them. The first discoveries in the 90s and the early 20s were from the radial velocity technique. You see they are all across the sky, both northern and southern hemisphere. Then after the 2007, 2008, the pace of the transit discoveries start to increase. You see more blue dots absolutely everywhere. And now there is a big chunk of planets that are populating this part, and there is a huge revolution in 2014. This is the Kepler field, the Kepler mission, who detected so many planets, more than thousands in this part. We also see some discoveries in this part of in the Milky Way, in the center of the galactic Milky Way, thanks to the micro-lensing technique, and see how the number has reached the 5,000 by 2022 in just about 30 years. So, but the planets that we have discovered, we can see that they are everywhere in the sky, and no matter what technique we use, we can detect them, but they escape our imagination because they do not resemble our own solar system. Here is a period mass diagram. Here is the orbital period of the planets and their mass in units of the Earth. That's why we have here Earth at 1 and 365 days, and the location of the solar system planets. And if we plot those 5,000 discoveries, we see that they occupy regions of the parameter space that, except for Jupiter, all of them are unknown. This is not telling us that the solar system is uncommon. Perhaps it is. What it is telling us is that we have a limitation in our detection techniques that is restricted to short period planets and more massive ones. We can see there is like a line. We could draw kind of a line like this in which our detection techniques stop working. We see that the majority of points are transit in blue, transit technique, and radial velocity in orange. There are some long period planets with masses close, even larger than Jupiter, that has been detected with direct imaging. And now the field is trying to move towards this direction, trying to be able to detect real Earth analogs orbiting sun-like stars. We know a lot of planets with the mass of the Earth, but at very short periods, no true analogs except for Jupiter. So how do we make sense of this population? Because understanding planet formation from first principles is really hard. We need to go from micron-sized grains to protoplanetary disks, in protoplanetary disks that grow all the way to a planet. So we need to cover around 12, 14 orders of magnitude in size and nearly 40 in mass. So doing that from first principles is really, really hard. And it takes a lot of interdisciplinarity to do so. So for the exoplanet field in particular, we've taken a demographic approach. And here we try to determine what is the frequency and the distribution of planets as a function of something that probably influences formation and evolution. That could be the star mass, try to know how many planets are as a function of a stellar mass or a stellar metallicity or distance. And we would like to create a function that tells us the number of planets under all these conditions to know what are these. And we would like to use parameters that are related to formation and evolution to try to understand how they form and why and where. So this is based on the hypothesis that the planet distribution actually would look like something that has relation with the planet formation. But there are probably many parameters that goes into this function, and probably will depend even on more parameters that we cannot actually measure. There is also the fact that planets migrate when they form, and that likely erases a lot of information that comes from the initial conditions. But also that we have different methods. You have seen different color points in the previous diagram, and each technique is sensitive and is able to measure some parameters and others not. So we cannot use one magnitude for all planets because some of them will not be amenable for some of the techniques. So what were the first steps in demographics? Were coming from the radial velocity surveys. You say that the first discoveries came in the early 90s and then the 20s. And here we can see just a crash course on radial velocity technique. Here you are measuring the wobbling of the star. This measuring back and forth due to the presence of a planet. It will stretch or elongate the wavelength. We create a Doppler motion that we can detect with a high resolution spectrograph. So the first result that came from here is telling us that for solar type stars, small planets seem to be at least an order of magnitude more common than the giant planets, that at short periods. Also, it's telling us that the frequency of giant planets, because it's the ones that we are most sensitive to, increases with increasing period. You see here, this is the occurrence of giant planets. These are the masses, and it increases up to more or less 1, 2, 3 years in orbital period, and then it decreases again. That location seems to be related with the snow line in the protoplanetary disk for a sun-like star, and then it goes down. So it seems like the forming giant planets at the snow line is something that is very common in other stars like the sun. And also we see that the occurrence rate of giant planets in short orbits increases as a function of metallicity, also as a function of stellar mass. So it's telling us that if you have a very metal-rich star that probably had a very massive protoplanetary disk, you will be able to form giant planets like Jupiter, more commonly in short periods. This is coming from mostly the early 2000 up to 2010, more or less. These are the results that we had. The only instruments that could give us demographic results were the radial velocity. But I show you that the transit keep up in the 2010s thanks to Kepler. And here we use the transit technique. So here you are monitoring the light of the star. You don't need an spectrograph as a function of time. And if you happen to be observing a planetary system that is in your line of sight, then you will see planets transiting in front of the star that will produce a decreasing flux. If you monitor this over time, you will be able to measure very precisely how long it takes to this planet to give a full round and measure the orbital period, and also how much light it blocks, and you can measure very precisely its radius. With the radial velocity, we were measuring the masses of the planets. With the transit technique, we are measuring the radius of the planets. But none of the techniques can measure the other parameters. So that's very important if we want to measure densities, because we need to combine both techniques. From transit alone, and from Kepler in particular, we found that the compact multiplanetary systems with regular spacing and size similarity are very common. You see, these are typical discoveries from Kepler. These are typical discoveries from Kepler, and this is what it's called the piece in a pod pattern. Piece in a pod, yes, obviously you know why. So they are very regularly spaced and regularly in size, okay? And also at very short periods. All those multiplanetary systems are typically in orbits interior to Mercury. We also found the existence of a hot Neptune desert, meaning that Neptunes are very rare in short period orbits, but short period small planets are really, really common, and even more if we do metal-rich stars. Here we are going as a function of metallicity, and we see how the occurrence of all short period planets start to increase. But the difference is very large. So even Jupiters, we have detected so many, inherently, they are not that common. They are more common, slightly more common for metal-rich stars. But if we are comparing to small planets, it is just way easier to form small planets in short period orbits. And for longer period orbits, the data, the error bars start to get bigger just because of sensitivity issues. But the most revolutionary discovery probably from Kepler was the radius gap. The radius gap, which shows that the planets with a size between Earth and Neptune, which we do not have any analog in the solar system, seems to be the more common in sun-like stars. So these are here the location of Earth, Neptune, Uranus, and the gas giants. And here is an occurrence rate. This is corrected from detection biases. That's why you see that even though we detect so many gas giants, it's just because it's easy. Okay, but they are not very common. However, we see that these two populations, this population between Earth and Neptune, is the planets that are the most common. Here we are not getting very sensitive to it, so maybe this starts racing again, and planets like with the size of the Earth starts getting very common again. But this population we are very sensitive to, and they seem to be way more common than, for example, Neptune's. Because of this bimodal distribution, we have classified this type of planets into two. These ones we call them super Earths because they are slightly larger than Earth, and this one we call them sub-Neptunes because they are smaller than Neptune. Not very original. But we have no idea what is their nature. Okay. There are two options here. We can have one option that is that the super Earths and the sub-Neptunes are the same type of planet. It would be an Earth-like core, an iron core and silicate mantle. And the planets that are in the left side of the gap, they don't have atmospheres. And the planets on the right side of the gap, they have atmospheres that are rich in hydrogen. This composition would be because they created the gas from the primordial disk. So mostly hydrogen and helium. These ones, in this case, the sub-Neptunes, we call them gas dwarfs, just like a gas giant, but smaller in size. Again, not very original. And then the second option is that the sub-Neptunes are a different type of planet. So they will be water dwarfs. These planets will have a very large water mass fraction, and it would be more like a scale-up version of the icy moons in the solar system, something like Enceladus or asteroids or comets that we see in the solar system that they form far away with a big amount of water. And because water is less dense than rock, these planets would have a larger size. With or without atmosphere, they will have a larger size, and that's why they are on the right side of the gap. Each theory can explain pretty well the observations, but they have enormous consequences, not only in the internal composition that I show you, but also what is their origin, where do they form, what is their evolution history. So in the first option, if we think that super-Earths and sub-Neptunes are just planets with or without atmospheres, but rocky cores, like the Earth just with or without a big atmosphere, this is very well explained by atmospheric evolution models. And you see how a simple observation, a very simple model can match the observations pretty well. Here, you are losing or not the atmosphere depending on how close you are to the star. If your star is emitting a lot of X-rays and ultraviolet energy, it will blow away your atmosphere if you are very close to the star. And that can lead to this, this population that is bimodal. There are many models that can include this. The heating, the way of removing the atmosphere can be done with heating from the star, internal heating from the planet, a giant impact. There are many ways, but the whole idea is the same. In the second option, you need to have, when you invoke global formation that occurs everywhere in the protoplanetary disk, it is very common for these models to form planets with a large water mass structure. These water walls would form beyond the snow line, where there is a lot of water. They will have probably a mixture of rock and ice in 50-50 proportion, and then they get massive enough to migrate all the way inwards where we detect them close to their star. This is a prediction that many models do, and also are able to reproduce the bimodal shape of the radius distribution with two different types of cores. This one would be a core like the Earth, and this one would be a water-rich core. That would be the water walls. Both reproduce the observations very well, but they have completely different predictions. And this is very important that all these studies have been done with Kepler. And Kepler is only sensitive, as I told you, to the radius of the planet. So we only know the size, and size matters, but density matters most, because you know which one to kick barefoot, right? Like, I mean, if you have a sense of the mass and the radius of the planet, then you will have an idea, a basic idea of their bulk composition, right? This is hard to do because we need to combine both transit and radial velocity techniques. But for M-dwarfs, there is a very nice opportunity, because we are able to measure the radius and the masses for a large number of systems, because thanks to missions like Kepler, was mostly focused on sun-like stars, and it was faint stars. But TESS and KEOPS were focusing on brighter stars. If you observe brighter stars, they are easy to follow up from the ground with radial velocity instruments, like Carmenes has played a huge role in this for the Endor host, but also HARS North, Espresso, Marunes. And this is a study that we did, that for the first time we did a demographic study, not in radius, not in mass, but in density. And we could do this for Endor planets because we had instruments that were sensitive enough to detect all type of planets orbiting Endors, Earth size or Neptune size, and everything in between. So this is a sample that we refined. These are all transiting planets as of the summer in 2021, all transiting planets with mass measurements orbiting Endors. And here we can see by eye that we can see like two trends in the mass radius diagram. This is a very intuitive plot. This is just radius here, and here mass. And here is the Earth. And if you plot on top, this is not a fit. This, if you plot on top the models from internal composition, very basic internal composition models, you would get one family of planets that seem to be all consistent with a density like Earth, and a bunch of planets here that are in line with a composition that seems to be related with a 50-50 proportion of ice and rock. This is contrary, or this was at odds with the current understanding from Kepler demography. The model that got the bigger track in the community was that the sub-Neptunes, these planets here, were actually gas dwarfs, that they were rocky cores with hydrogen atmospheres. But we see that it is impossible to reproduce this uniformity in density if you plot them, if you let them have an atmosphere that can be influencing its size a lot by just the water, by the atmospheric gas mass fraction or the temperature of the planet. There are many factors that would create here a lot of scatter. But this uniformity is very difficult to reproduce with those models. Here we can plot it in a different way. We can normalize the densities. And if we normalize the densities with respect to a model like the Earth, here now we have the green line centered around 1. And we would have here a family of rocky planets. And then we have here another family consistent with this water wall component. And then other planets that seems to be way less dense, that necessarily have hydrogen atmosphere in order to explain their sizes and their relief. So what we see is that what it was interpreted as a radius gap is not representative as composition. Here we have the radius again as a function of the number of planets. And here we have still the shape, but the shape is not representative. The planets that are falling in one of each or the other side are not representative of the composition. Well, if you plot them in density, if you just see an histogram in density, you have the families very well separated. And probably this family and these ones are the same, just with the addition of hydrogen on top of this course. When we publish this result, we compare with models, and it was the data was agreeing very well with the predictions from planet formation models. Here it is a simulation. These are simulated planets from a model that takes into account formation from the very beginning, from the protoplanetary disk, using planetesimal accretion. But this one, for example, is using pebble accretion. And you can see that when you take into account photoevaporation, these pink and green points, you can reproduce pretty well this trend of planets here that are rocky, that are consistent with the observations. Then another family that is very uniform in density. And then when you start getting higher in size, those planets start to take off because you are adding hydrogen. And that would be like a continuous line all the way to the Jupiter-sized planets. So the observations were agreeing very well with planet formation models that actually include photoevaporation. So photoevaporation is an ingredient that is necessary, but these planets have a water mass fraction that is close to 50%. You can see here, they are blue. So these planets necessarily need to form beyond the snow line because they cannot get enriched so much just by pollution from planetesimals or pebbles or impacts or something from beyond the ice line. They necessarily need to form beyond the ice line and move inwards when we are detecting them. Here we are restricting our sample to 0.15 AU, so we are really near to the star, and these planets cannot get there with those water mass fractions if they don't form outside. But there was a new recent study that was published counteracting this, and they update the models of the gas wars. They include a phase that is called boil-off, in which the planet is accreting the atmosphere in the protoplanetary disk, but when the disk dissipates, there is an instability there because there is nothing to contrast the gravity with the pressure. And then most of the atmosphere that has accreted by the planet, when the disk disappears, it blows away. And if you take into account that in the models, you could have rocky cores with hydrogen atmospheres that follow this trend, both in photoevaporation and core power mass loss, this internal heating thing. That would reproduce our observations. This is a very new study. And yeah, here we have a problem, right? Like there is absolutely no hope if we do mass radius diagrams. Well, the new hope is the atmospheric characterization. It seems to be possible, at least from a theoretical point of view, to distinguish between a rocky core and a massive hydrogen atmosphere, the gas world scenario, because of the components of the atmosphere compared to a rock and liquid water layer or a water-rich core interacting with a small hydrogen atmosphere. Here we see a simulation of in a typical wavelength range from James Webb, where there are some features that would be different. For example, ammonia, CO2, methane. They could have the atmosphere of a planet that is a gas dwarf, meaning a rocky core with a large hydrogen atmosphere, or a water world, would have different features in transmission spectroscopy. This was all theory and coming from a few years ago. And now, for the first time, we have some observations of sub-Neptunes with James Webb. And this is one of the newer ones, K218b, a very famous sub-Neptune that have a detection of water in this part of in this wavelength range with Hubble. This water detection has been confirmed to not be water, but actually be methane. The detection of methane in a small planet is the first time that it's done. That's already an impressive result. But not only that, there is a detection of this thing here, DMS, which is dimethyl sulfide. That's a biomarker in it. So this is a tentative detection that can go away if you start playing with the data, adding offsets and try to get rid of it. You can get rid of it below 3 sigma. But this is just one transit with James Webb. So if one transit with James Webb for a sub-Neptune can detect a biomarker, or a biomarker at least on Earth, we don't know if in these planets this chemistry will be the same. This is really promising. This is really promising. K218 would be compatible with this water wall. This methane atmosphere would be only possible if below that hydrogen-rich atmosphere, because it's one of these planets that were falling on top of the curve, has only a liquid ocean below. The temperature of K218, the equilibrium temperature is around 300 Kelvin. So it has like temperate conditions. This is the habitable zone of the star. And this composition of the atmosphere could only be explained if it is interacting with a water liquid ocean below. The other observation that we have for a hotter planet is JWST. For JWST, we have a very flat transmission spectrum from Hubble. That has been confirmed also with James Webb, extremely flat across all wavelength ranges. But when you look at the secondary eclipse and the phase curve, when you look at all geometry in all 3D orbit of the planet, you see that the planet likely is also a water wall. It has a very metal-rich atmosphere, and those metals seems to be likely water. So also it has a huge layer of clouds and aerosols. That's why the transmission spectrum and the emission spectrum is so full. But the few tentative, the few measurements that we collected so far with James Webb, they seem to point towards this direction. So what is the present and the future for sub-Neptunes? Atmospheric characterization together with densities, because we need masses, very precise masses and very precise radii for these planets, seems to be like our only chance to observationally test this hypothesis. But we need also demographic studies. And transmission and emission spectra is really complicated, especially for this planet. We are the forefront of what James Webb can do. It is very tough to distinguish between an actual featureless, high molecular weight, meaning an atmosphere that is hydrogen rich, but it has so many clouds and aerosols that the transmission spectra is flat, than having an atmosphere that is water rich, and because it's water rich, it is heavy. It's way more heavy than the hydrogen, and all the features, even though it has it, they are shrinked. So this is complicated. I think it will take a lot of modeling, a lot of understanding of clouds and hazes and aerosols in this type of worlds. We need precise and accurate masses for these planets. We cannot just measure them if we only know the radius. We need to know their masses, because in order to interpret the transmission spectra, in order to interpret their atmospheres, we need to know the gravity of the planet. The gravity is something that we need to fix. If we include it in the model, then we'll have degeneracies that can compensate for a lighter atmosphere or a heavier atmosphere. Also, we have here an observability cut, a bias. We will be able to do emission, meaning observing the secondary eclipse when the planet is not seen. When the planet is directly seen, excuse me, we could do that for hot planets because we are looking at the emission from the planet. So hot planets, they get favored. But transmission in the primary transit, it will be more favorable for the colder ones. And for those, we probably will do them only for endors. And endors have a lot of problems, like stellar activity and other things. But these planets really represent an opportunity to find habitable conditions now. It is not in the future. We don't need to build habitable worlds or life or nothing. It is now. With James Webb, one transit, we can get tentative detections. So this is really promising, because we are sampling a much more accessible part of the parameter space. The same that we did with endors to look for Earth-like planets and detect Earth-like planets, we should do with water worlds to look for biosignatures. It's something that we can do now without the necessity of new missions. And then we will move to Earth-sized planets that James Webb will not be able to do. So in terms of the small planet demographics, the future is also good thanks to PLATO, because age is one of the few parameters where these theories are predicting opposite dependencies. So planet frequency as a function of size and distance and age is something that the models from gas wars and water wars have different predictions, and PLATO will be great for doing that. That will be for the first time, actually, that we will have precise ages for thousands and thousands of stars. And then not only James Webb, but afterwards ARIEL will be able to detect a small planet atmosphere and do it in a demographic way, do it for hundreds and hundreds of planets. But what about the long period small planets? Because long period small planets like Earth, for example, it is really challenging to do it with radial velocities and transit techniques. So this part of the parameter space will still be empty if we restrict ourselves to radial velocities and transit. But there are new missions. For example, habitable worlds with direct imaging will cover this part. The ELTs in direct imaging also will probe the long periods, and Gaia will fill also this gap here. So in the astrometry, direct imaging, microlensing will be very good, will become very relevant, even though the numbers right now are very few. It will increase by orders of magnitude the detections from this new data. So coming soon, we'll have family portraits where we can just point at a system and detect all the planets in a system and get atmospheric observations of them at the same time in one shot. And we'll be able to compare and combine transit and microlensing demographics to get a better feeling of how occurrence rates of planets go as a function of distance. So in summary, the small planets seem to be ubiquitous in the galaxy. They have no counterpart in the solar system, but they are really more common than giant planets. They seem to be more common at short periods if they orbit metal-rich stars. They are more common among the least massive stars like N-dwarfs. And they seem to be multiplanetary system, compact, with regularity in size, with regularity in space. Also, the sub-Neptunes still are a mystery. Perhaps the water world hypothesis is the one that is reconciling better the current modeling and global formation efforts from the modeling perspective, and these new detections in James Webb seems to point into this direction. But gas wars too, if you fine-tune the models, you can reproduce the observations too. So James Webb, PLATO, ARIEL will really provide very valuable information, mostly the ages, the atmospheric composition that can break the degeneracy that we see from mass and radius alone, and perhaps close the debate within this decade. And also, our knowledge of demographics is really driven by radial velocity and transit surveys, but new missions and new techniques are going to become very relevant in the future. So that will increase the number of discoveries, just not by a few, but by hundreds, by orders of magnitude. So combining different techniques and doing demographics using different techniques, which is very challenging because I told you that they probe different parameters, they measure different parameters. So this is going to be a way to move forward. And here I'm going to let you with some final thoughts on sub-Neptune science. And it's that the candidates in this part of the parameter space are really precious because they need to be transiting planets. And transiting planets, we have been observing the sky long enough, and we have been surveying the solar neighborhood long enough to mostly have detected all of them that are in the solar neighborhood. The transit geometry is very particular, so we are restricted to very few systems that can show us a favorable geometry. So we are going to have just a few hundred planets that are transiting and that are orbiting stars that are bright enough to measure their masses. And if they are bright enough for their masses and their radius, we probably can do also their atmospheric composition. But understanding sub-Neptunes, it will improve our understanding in other areas. It will be for global planet formation models. Is it very important migration or not? Are these water worlds really common? So we need to migrate planets from all the way beyond the iceland, or do planets form in situ mostly? What about internal composition? We see this type of compositions in the solar system, but do those planets with those compositions can really grow that much? What is the connection between the internal structure and the atmosphere? These planets, some of them are so close to the star that they are hot enough for their rocky core to be molten. So you are having an interaction between a lava world, a magma ocean with the atmosphere, and those type of chemistry will alter the composition of the atmosphere. also about planet evolution. Is it how important it is for the evaporation, internal heating, giant impacts, all those things are very important. Atmospheric characterization and modeling, because it's very tricky to distinguish between these observations. But James Webb, we're not going to get anything better than James Webb. ARIEL will be less sensitive than what James Webb can do. So otherwise, we'll need to wait until missions like LIFE in the 2050s. And also for astrobiology, because it's a shortcut. It's a shortcut to do biomarkers now with current instrumentation without needing to develop new. It's true that the planets will not be the same. These are planets that are twice the size of Earth. They are closer, but they could be in the habitable zone of their host stars. And this is already very interesting. So all these processes are really important. They affect each other and they cannot be addressed separately. This is a necessarily multi-technique and multidisciplinary field. And that's why we are making a conference in Germany. This will happen this February, which I'm organizing with Remo Brandt from Max Planck in Heidelberg. And we are going to bring the expertise from people that are working in the formation, internal structure, atmospheres, evolution, to work for the first time, trying to combine this expertise and develop new models that can accurately reproduce the observations that we are starting to get. So I will leave it here. You want to know what is this place, you can ask me later. And thank you very much. I'm happy to take any questions.
So we can have questions now, I guess, and maybe quite a few. We go here first in the room, and then later we see if we have any online. Well, here I saw Matilde first, and then Alex.
So, thank you very much. I wanted to ask you, you have mentioned that some models involve time, in the sense that they need the atmosphere to change or something in the planet to change. Do you think that these times and timescales match the ages that, for example, PLATO or maybe also the missions are going to provide, and the precision that they can get for ages, or it's not yet much better?
For example, for the gas to orbit scenario, like if you want these planets to be rocky with or without hydrogen atmospheres, the time scale in which you remove the atmosphere, it is, depending on the mechanism, either shorter than 100 mega years or larger or on the giga year scale. So that's something that, for example, PLATO will clearly be able to prove. For the water world scenario, time is not as important because the migration will happen much faster. These planets, they need to be massive enough and form beyond the snow line, form quickly enough that they can migrate before the disk disappears. And the disk disappears, and this happens very quickly. So actually, the axis of age for atmospheric composition will be very important because there will be a gradient in chemistry processing. So atmosphere should get more metal rich with time because of processes with the internal structure, pollution, impacts. This is something that will be more in a more gradual scale, but those differences from shorter than 100 mega year to on the giga year thing, clearly PLATO will be able to prove.
Okay, thanks, Matilde. Alex, you have one?
Yeah, I had a comment and a very small question. The comment is that indeed we pretty much sampled all the transiting sub-Neptunes close to the Earth. But we have another advantage, which is that at high resolution we can also probe atmospheres for non-transiting planets like JWST. So yeah, just a comment. We may be able to expand that a little bit. And then I'm still, we've already discussed about that, but I'm still puzzled by the K218b composition, especially with the water features that are now turned into methane features, because do you know the authors actually retrieved or estimated the C2O ratio, and if that can provide any information formation condition?
Yeah, they don't have an independent oxygen molecule. So because they don't detect water, they cannot measure C2Os that are reliable. So also the data is not public. and nobody else can do retrievals on this data. So, well, I mean, there are many models that have been produced for K218, and there are some models for actually rocky planets with very metal-rich atmospheres that are, I think, carbon-rich, that can reproduce the observation, but that's just by eye, that they seem too much, but the authors do not do a retrieval.
Okay.
Anyway, this is just the first time. It's gonna get observed way more, and as soon as the data becomes open, I'm pretty sure a lot of things.
Yeah,
want to
it's a
retrieve.
little bit frustrating that a water world does not have water.
Yes, but that's actually, in this case, the planet necessarily is larger. It's one of those that we see in the upper part of the diagram. It cannot be matched by just a water-rich core and a very thin atmosphere. It necessarily have this size that is increased by hydrogen rich. But when we define in this water world, what we actually meaning is a planet that has such amount of water that necessarily needs to form beyond the iceland, right? Having a small amount of water, it is possible when you form in situ in the short periods. But here, yeah, I mean, the nomenclature is just very tricky. You could call Earth a water world, and clearly it is not. Just by mass is 0.1%. For even less. Here we are talking between 20 and 50% water mass.
Okay, thank you. Very nice.
Yeah, thank you for the talk. I have a question on the Kepler 2 architecture planets. I think one of the future there is when you look at this right, it's like it seems like super Earths always come in couples, in doubles, in the systems. So is it a coincidence? Is it a bias? Or is there an explanation for that? And
what do you mean here in super Earth coming couples?
well, like yes, if you look at the first couple of exoplanets, their systems, the big super Earths, the big circles now.
Yeah.
So these are super Earths, no?
No, these are actually almost Neptune planets. So this is just the circle scale, the size scale is just very uniform. Here you cannot appreciate.
It seems like they
they are all coming in this. You could say in pairs. Yeah. I mean, if you do simulations in which you take into account, you are tracing from synthetic models, you are tracing the water mass fraction, you would see that the inner planets in a given system typically are rocky, and the other ones are water rich. And it just comes as migration. You are migrating all things together. You get trapped in resonances, and then afterwards you break them. So the spacing is very regular, and probably just from a couple of planets in the interior of the snow line, a couple outside, and then you migrate them. Maybe it's those pair things.
And why don't we have super Earth in our system?
Sorry?
Why don't we have a super Earth in solar?
Maybe because we have a Jupiter. So it seems that when you do the conditional occurrence rates as a function of the presence of a gas giant, the occurrence rate of super Earths decrease. So you have less systems with super Earths if there is a Jupiter somewhere in the system. So it seems like the formation of gas giants really affect a lot the architecture of the whole system. And if you can think about that, like normally Jupiters, they form, as we see previously, they seem to form here around the snow line, more or less. If you form here a Jupiter, you create a gap in the disk. So whatever you are forming beyond that is not going to be able to migrate. These planets may exist. There may be water worlds there. I mean, we have Uranus and Neptune, but these are so far away that we don't have the sensitivity to detect them. And they cannot migrate all the way to these short period distances where we are measuring them. We are limited to short period small planets. And in order to get short period small planets that form beyond the Earth line, we cannot have a gas giant forming before the sub-Neptune. It needs to form after in order to migrate in time. So it's just a conditional thing. It's something that demographically could be tested when we have more observations and with longer baselines.
Okay. we have Fran, Gabriela, and Maya.
Okay. Thank you, Rafa, for this super nice talk. I was wondering, well, about the biomarker that you mentioned in K218. The first question is, which is the source on Earth to produce this gas? And the second question is, which is actually, can we be sure actually to expand or extrapolate a biosignature on Earth to be also a biosignature in a sub-Neptune? Is something straightforward to do? Or?
I don't know. I don't know how it is produced on Earth. First thing, I just read about it. Maybe plants.
Plankton.
Plankton. Okay.
Okay.
So yeah, it matches actually the ocean thing.
Yeah.
And the other part, the extrapolation, is the same about habitability of Earth-like planets around M-dwarfs. Are M-dwarfs because of their stellar activity having so many flares that will start biology or will completely kill it? You don't know. There is a fine balance there, and we don't know here in this type of planets. I mean, we are gonna go to Enceladus to check for things like that, right? And that's not a planet like the Earth. That's a small body that has water, and we are interested in checking that. Here is a large body with a lot of water. So, I mean, there are the studies of Earth global oceans. They don't seem to be good for life. You need to have like some small islands or something like that for doing the chemistry in a kind of a pond. I think it is like you need some sort of shallow ponds of water surrounded by land in order to get silicates and stuff like that you need to kick off this prebiotic chemistry. Maybe in these global oceans that's completely impossible, but this is something that needs to be explored now. This is first, let's detect them, let's identify some candidates, and people doing modeling will try to sort this out. Thank you.
Thanks, Rafael. My question was back to the demographic side. How planet formation model can explain the fact that small planets are more common than hot Jupiter, because I guess most of them are hot Jupiter around metal-rich stars. Is there an explanation?
It seems to be just you have a more massive protoplanetary disk, so you are able to form more bodies, and forming smaller bodies is easier than the larger ones, and you can form them in situ, like in the closer regions, or you can migrate them from beyond, because there is a lot of material available. I mean, planet formation apparently is very efficient. We don't know how to go from micron to planet size, but or exactly the mechanism, but whatever works, and it works everywhere, right? There are more planets than stars. So that's something that we know it works.
Because of the environments.
Exactly. Yeah. And that's why you get these trends with the as a function of a stellar mass. The more massive the star, also the more massive the disk. The more metal rich the star, the more massive the disk, more dust, more things that favor accretion, coagulation, accretion, all these processes. The mechanism exactly is not clear, but it seems to. Those are the trends, right? Those are the trends. The only thing that we can trace this back to something.
Planets around the research work already.
Exactly.
Yes.
Exactly.
Yes.
And it is confirmed when we got sensitive to smaller planets, it just the trend continued.
Thank you for the talk, Rafa. I had a comment and a
Yes.
questions. I don't know if you are aware about new technique by radioastronomy to detect exoplanets. The research try to measure astronomy using very precise observation with techniques of VLBI array, and they try to detect perhaps so far two exoplanetary systems. One of them has a very small star surrounded by a Jupiter mass protoplanet. Perhaps this technique will populate the demographic diagram that you have shown.
Yeah.
I don't know if you can say some.
Yeah, I think it will populate mostly this region. So will be will be able to be sensitive to periods or on the order of several AUs beyond the distance of Jupiter. But maybe with SKA or something that the resolution can get improved much better, maybe we can start actually probing areas like the where at 1 AU or something like that, depending on the distance to the star. So I think this is a very promising thing. And actually it can tell you where planets form in a disk. Where do you see the rings? Where do you see the gaps? And they are early or young enough to have some constraints into if they are going to be able to migrate or not afterwards. So I think it is very, very interesting. And all the observations in protoplanetary is also the chemistry of the disk is very important in order to know if there is what is the material there, because it's gonna be the planets that form in that area is gonna carry out that composition. So yeah, I think that is very promising, and the new instrumentation seems to be even better.
And my question is about the photoevaporation process that we have mentioned, which is, I don't know if I understood well you referring to photoevaporation from the star, photoevaporation for the reprocessed emission from the disk itself, right?
Yeah, it is a very bad name. I think naming in general is very wrong here in exoplanets. Yeah, photoevaporation is like a Parker wind that blows away the hydrogen atmosphere that will be maintained by gravity by the planet. So after this dispersal, the planet is there surrounded by nothing, and that if it holds on to an atmosphere and if it is too close to the star, the Parker wind from the sun, it will remove that atmosphere in timescales of a few mega years. If this is not the case, if photoevaporation that mostly comes from XUV photons, it is not that important. Another source of energy seems to be like the internal heating of the planet. The internal heat from formation, the planet when it's still hot, it will be blowing away, create its own Parker wind, and you will reduce the boundary radius of the planet, so everything beyond that it will escape, right? So that's what would be. So photoevaporation is a very bad term, but it's just more like a Parker wind, or yeah, if you are bound by gravity or not, if your boundary radius is smaller or larger than your atmosphere.
Okay, any other question here in the room? Because we have one online. Miguel Perez Torres, who can read it?
I can.
Okay. Matilde has another question. Just in case.
Well, you look for this question, but you didn't have it.
She didn't write. Miguel?
Oh, yes. Okay. You want to ask a question?
Yeah, you open the mic, but you cannot hear me. I just show this is open.
Okay, can you hear me now?
Yes.
All right.
If Miguel
so-
cannot hear you, maybe you can
All
write
right. Okay, I'll write it.
Can you try again?
Okay.
Can you hear me? No?
Yeah.
Oh, yeah, but there is the return, I guess. Sorry, so very quick. So Rafa, could you clarify in this, well, by the way, very nice talk. Could you clarify this thing about the short period, the small planets being more common? Because I think from the plots, it looks like the larger periods are more common in terms of number of planets per 100 stars. So I got a bit confused.
Yes. Yeah. So I think it is just when we see the other plots are sensitive only to gas giants, and gas giants seems to be more common as a function of distance. They peak at around the stone line. For the small planets, we don't have the sensitivity. You can see already in this diagram. We don't have the sensitivity of measuring small planets that have a period slightly larger than 100 days. So we don't know if this occurrence rate peaks here and then decreases again or not. In this other plot, it seems to increase as a function of metallicity, but this curve is lower than the 10 to 100 days.
Do you have a cursor in the, or the
Yeah,
cursor
I-
of the computer? Because
yeah.
I cannot see your.
I don't think I can show it. Yeah. Okay. Well, you can see in that diagram that the blue line and the green lines are higher for the 10 to 100 days than the 1 to 10 days, but the error bars start getting larger, and it's just way more tricky to measure this.
Okay, I understand. Well, I
Actually,
will say then,
that it increased, and we would expect that if they are water walls, you would expect the occurrence rate of water walls to increase as a function of distance, because they need to migrate less, and it doesn't matter if there were super Earths in the interior or not. For sub-Neptunes, also for the gas dwarf scenario, you would keep them larger because they are so far away that the XUV photons from the star, the particle wouldn't reach there, so they would be able to hold on to the atmosphere. The explanations are all very degenerate, so really every model can explain everything if you do enough assumptions.
okay, yeah, but so thanks. It's just that I think that maybe the plots are a bit confusing.
If I may ask you,
Yep. That's question.
so you mentioned at certain point that the activity of M stars are rather different. So to go to stars that are a bit more massive, I guess, K stars, B stars, and then they also have activity. So my question is, with which precision do you want the parameters of the planets when talking about this one that orbit K?
For the atmospheric retrievals, you should have at least a 20% mass precision in order to derive a good surface gravity that it's not influencing your retrieval. That's like a value that we normally take into consideration. But regarding the stellar activity, it's worse for M dwarfs than for the K and the G. But the problem is the radius ratio that we are still observing in transit. So for the same size of the planet, if we are making the star larger, we are going to start losing precision, because the same planet is going to have a smaller feature if it is orbiting a G star than if it is orbiting an M dwarf. So the larger the transit depth, the more variation, the more sensitivity we have in the variations as a wavelength function inside that level. If we stretch the transit depth to a G star, it's very complicated to find those relative. Our precision stays the same. I mean, with James Webb, we are going to have the same precision. We are going to be able to detect perhaps like 20 ppm features, 30 ppm features. But if that's on a baseline of 1,000 ppm transit, that's pretty good because we have a lot of signal. But if that's on a baseline of 100 ppm transit, then the relative errors are much larger.
Okay, any other questions for Rafa? One over there. Go ahead. Yes.
Also, the last video.
Yeah, so I can put. So this is what Anchon said about the observatory that we have developed in Gorafe. It's now working. Here it is the control room and our library. These are the toilets. Here there is a theater for activities, and these are our domes. Now we have in each dome we have a telescope. Actually, we have contributed already to a paper from Jose Luis Ortiz here, doing an occultation, a stellar occultation with our 3 telescopes that were there working. So yeah, it's been working for a year now, and you can check the website, subscribe to the newsletter so you know what our activities we are doing every weekend. But it is very nice. It's in Gorafe, it's just an hour drive from here. The sky is great. The region is now being declared UNESCO Global Geopark. So there are a lot of trekking activities and things to do in all these villages. You can eat great in that area. It's in Cordero Segureño. And yeah, this is where I've been working. We're very happy after so many years working in the area. We can have our own space.
That's very nice. Yes, indeed. We visited.
Yeah.
When was that?
Last year. Yeah, it was the first time actually that nobody came before that. It was for the Exoplanet Science Congress that was celebrated here.
In some.
Yeah, now it has telescopes in the domes. Before it didn't have. It had only telescopes here outside.
That's good.
So
Are you selling the observational lines or, I mean, are open to the community or something?
We are right now controlling ourselves and we are roboticizing everything so we can control remotely. But yeah, the idea will be renting the telescopes that people can use it for astrophotography or whatever they want to do. I mean, it's devoted to astrotourism outreach and everything. We have been doing some science for fun, but the idea also that other people can make use of the telescopes. Now it has a glamping here, so you can even spend the night. So.
Okay, well, if we don't have any more questions for Rafa, let's thank him again for a very nice talk. I have two things to say. On Wednesday, we will be giving an informal presentation on some results we have been coordinating for the past many months. We will